All right, so we did look at this last year in Year 12, and we're just really revising what it actually means to make sure that as Year 13s we understand what we're talking about. So what we need to understand is that when we are differentiating, at all times we are looking for the rate at which something is changing. All right? We have dealt majorly with the fact that our first derivative has been about a function or a graph, and that our first derivative is looking at the gradient. The gradient is the rate at which the graph is changing over the period of x. All right? So if you take that and you apply it to any situation, lots of things change over time. All right? You can have things that shrink, you can have things that grow. It doesn't always have to be over time. Things can change with respect to something else. Now, this is why the notation of d something by d something is a better notation than a y dash or an a dash or anything else, because it actually tells you what is changing with respect to what variable in our formula. All right? So we may have something, the first derivative describes the rate of change. So a couple of examples, we've got dy by dx. This is basically talking about the function of y, usually related to a graph. Not always though, it can be a function without a graph. So the rate, the function of y changing over x. So that's as we go across the graph, what is happening. It's going up, it's going down, it's going somewhere else. So that's the rate of change, all right? We could draw everything as a graph. So this one, the area of a circle changing with respect to the radius. If we had the area of the circle on the y-axis and the radius of the circle on the x-axis, we could look at how it changes, right? Because we know that the formula for the area is pi r squared. So if we start at 0, we haven't got a circle. But the moment we leave 0, we are starting to drive an area, all right? So therefore, we would have it as the rate, the area. In this particular circumstance, it's a circle because there's an R in it. Right? So something like that. These are simple rates of change. So the likelihood in this sort of question is that you will only have one thing changing. So you might have the rate at which the volume of something changes by the height. That means that all of the dimensions of whatever the volume thing is that we're finding have been put into the form of a height. So the height might be twice the length, which is 3 times the width, all right? So now we've got h for all of them. They're just different h's. We put them all together, times them all together, we get a volume. But if we change the h, what will happen to the volume of this whatever I just described a rectangle, but that rectangular prism, so that would be what we would be changing. Do you get it? All right? So this one would be the volume of something changing as the height changes. But in these very simple ones, we'd have every dimension written in h. All right, so an example of that would be what I said. So width equals 2h, length equals 3h, and obviously height equals h. Something like that, so you get that term. All right, so those sort of things are what a rate of change is. It's just differentiating whatever our topic of conversation is and finding out the answer. So the answer could be that we're putting R in. What's the rate of change? What's the rate at which the area of a circle is changing when R equals 3? Put 3 in to the derivative. Yep. What is the radius when the area is changing at a rate of 3 meters per second, whatever it is? So that means we've got the 3 as the area derivative, and we're trying to find out what radius is. So we've got both ways, just as we have with the gradient equals at this, or the gradient is what's the x. Those two forms of questions. So the most common thing that we use this for is, okay, good, physics. As soon as I write that up, everybody goes, oh, physics. Now, it is physics, but it is maths, and the difference between the physics and the maths is that when we're dealing with it in physics, unless we have done the maths to be able to use it, we are finding an average rate of change of things. So we're finding the average speed between here and Palmerston North. All right, so how long did it take us to get there? I mean, how far have we travelled over? How long did it take us to get there? All right, or the acceleration, how fast were we going? What's the change in the speed over how long did it take us? So that is the average, and that is what we deal with in physics and mechanics. I don't know. But in maths, we're talking about instantaneous. How fast are we going at this point? What is the acceleration at time equals? And we can do that because if we're given that original formula or any part of the formula, we can anti-differentiate or differentiate to find the parts and be able to substitute into it. And substituting into it gives us an instantaneous change because we've modelled whatever is happening on a function. All right? So we've got to rely on the function being accurate to be able to do it, but that's okay too. So with kinematics, we get those 3 letters, S, V, and A. All right? Distance or displacement. Remembering that displacement has negatives and distance doesn't. Velocity or speed. And acceleration. It's important here that we remember our units. So we've got, if this was in meters and our time was in seconds, then we would be writing this or meters per second. Meters per second squared. All right, so we've got our units involved in it, and we know that we can differentiate to get the next one. Now, because there is so much in the differentiation topic, these questions tend to be in the integration topic, which isn't necessarily right unless you can actually, acceleration is where you started. Because the difference between integration and anti-differentiation is that anti-differentiation is taking you back to the starting point. So we differentiated to get here. We anti-differentiate to go this way. That is the same process as integrating. But the process for integrating says we started here and we integrate to get to here. We didn't anti-differentiate. We went forward from a particular function. So we didn't start with the derivative. Anti-differentiation, we start with the derivative and we go backwards. But all of that testing comes into the integration standard. So this question usually comes in the integration standard. But if they stuck to only being a this way question as a rate of change, it could be in the differentiation question standard. All right? Can you understand? All right? So let's have a look at an example. A simple example would say something like distance is measured by g of t equals 5t cubed plus 3t. Hello. What is the rate of change when t equals 2? Alright, so just the same sort of questions as you had last year. What do? We take that rate of change says differentiate, so we differentiate and we chuck 2 in. dt by d. Big D. Change it to big D so that we know the difference. T equals 15t squared plus 3. So when t equals 2, dt and d equal 4. 4 times 15 is 60, 63. And we'd have some sort of units in it. So t would say seconds, and this would say meters, and we would get meters per second because we're doing a rate of change. All right? So that would be this sort of one. This one could be an A one, but it is just a case, these particular ones are easily differentiating and substituting in. Remember, though, that we can go the other way. So they could have asked here if the rate of change is 15 metres per second, when did this happen? Then you're finding t. All right? And you've got to remember all those other words too, like initial time, t equals 0, constant, no variables. All of those sort of little bits of information also apply to these. Okay.